All right, last video for chapter 20, we are going to be talking about electrolysis, which electrolysis is when we use electricity to force a non-spontaneous chemical reaction to occur. So if we add up the voltage for our two half reactions off of the standard reduction potential table, and let's say we get a value of negative 1.5 volts. What that means is that tells us our reaction is not spontaneous, and we would need to provide at least 1.5 volts of electricity in order to force the reaction to occur. So what we're going to do is we're going to look at some of the vocabulary associated with this, and then we're going to do a couple of example problems. And then we also are going to figure out if we need, say, 1.5 volts in order for that reaction to occur, how that's going to relate to current and amps. So this does bring in some of the stuff that you should have done in physics with electricity. As a review from Regents Chemistry, in a voltaic cell, that is our spontaneous cell, the anode is negative and the cathode is positive, and it is transferring electrons spontaneously, so therefore it is producing volts of electricity spontaneously. When we have our electrolytic cells, oxidation still occurs at the anode, reduction still occurs at the cathode, but because it is going to be hooked up to its own electrical source, like a battery, that will change the charges. So in our electrolytic cell, the anode is now positive and the cathode is now negative. But electrons still flow anode to cathode, oxidation still occurs at the anode, reduction still occurs at the cathode. The charges change because it is hooked up to its own electrical source, like a battery, which then causes the charges to revert. All right, so on our electrolytic cells, again, they are not spontaneous, so they would need an external source of electricity, and they have a negative cell potential. So when we add up the two half reactions off of the table, we would see a negative voltage. That means that they will also have a positive delta G, and K would be less than 1. So here is an example, the electrolysis of water. So this reaction here, water being decomposed into hydrogen gas and oxygen gas. Now, common sense is going to tell us that that is not a spontaneous reaction. Water does not spontaneously break apart into hydrogen gas and oxygen gas. So common sense would tell us that this is probably not a spontaneous reaction. If we look at the two half reactions that would occur, and then if we find those two half reactions off of the standard reduction potential table, we would get a cell voltage of negative 2.06 volts. So provide at least 2.06 volts of energy in order to force the reaction to occur. Again, oxidation is going to occur at the anode. That never changes. So we still do have an oxidation occurring at the anode because we have a loss of electrons. And at the cathode, that is still going to be reduction. We know that this is a reduction because we have a gain of electrons. And that brings up an important point when we have these more complicated half reactions. It's harder to tell what's happening based upon just the oxidation number. So you have to look at whether or not electrons are being lost, that would be oxidation, or gained, that would be reduction. All right, we're going to be doing some calculations now where we can figure out if we have a certain current running for a certain period of time, how many grams of that compound or element will react. So this is really just going to be some stoichiometry, and then we also are going to be using a formula off of our reference table. So if we take a look at the bottom of the thermochemistry, electrochemistry section, we have an equation that says I is equal to Q over T. And you will see that I is current, that's going to be measured in amps. Q is charge, which will be measured in coulombs, and T is time, which will be measured in seconds. If you have done electricity and physics, this will be familiar to you. All right, here is our first example. So how much calcium, that should really say how many grams of calcium, will be produced in an electrolytic cell, so we know it's not spontaneous, of molten CaCl2. Molten means that it's a pure liquid. So we have CaCl2L, not aqueous. So therefore, this is occurring at a very high temperature because since it's an ionic compound, it would have a very high melting point. If a current of 0.452 amps is passed through the cell for 1.5 hours. Okay, so first off, we write our equation. So the calcium chloride decomposing into calcium metal and chlorine gas. So this is not something you would want to stand around and watch happen because chlorine gas is toxic. All right, that's already balanced, so we don't have to worry about balancing that. If we wrote out our plus 2 electrons will be reduced to the calcium metal, and 2 chloride ions turn into Cl2. That would be an oxidation, and there would be a loss of 2 electrons. So the reason why we need to do that is because we do need to know the number of moles of electrons that are transferred. So that is very important to know. So the first thing that I do is I start with that I equals Q over T formula. So I is going to be my current. So that is going to be the 0.452. Q is going to be one of the things that I am solving for, and that is going to be in coulombs. And then T is time, but it does have to be in seconds. So 1.5 hours. So you have 1.5 hours times 60 minutes times 60 seconds. All right, that would give us 5,400 seconds. So now we do our math, and that would give me 2,440.8. And that is going to be coulombs. Then what I'm going to do, and you could do this all in one step if you wanted to. So now I take that answer that I just got and do some dimensional analysis. So I know I need to get rid of coulombs. That's where I'm going to use Faraday's constant, 96,485 coulombs per 1 mole of electrons transferred. So that's important to remember that Faraday's constant is coulombs per mole of electrons. And then in order to cancel the moles of electrons, 2 moles of electrons because 2 moles of electrons are transferred in my reaction. So if the calcium was gaining 17 electrons, then 17 electrons would be going in our denominator there. So 1 mole of electrons for, or 2 moles of electrons for every 1 mole of calcium. So now that's going to have us at moles of calcium, but we were supposed to get grams of calcium. So then we multiply by the gram formula mass for calcium, which is about 40.1. And so then my coulombs would cancel, my moles of electrons would cancel, my moles of calcium would cancel, and I do all of my math, and that will give me my answer. So we pick up our calculator. And I get 0.51 grams of calcium. Now, if you had already rounded this number here, then you might end up at 0.50, but we should be at about 0.5 grams of calcium. So hopefully you see that this is still basically stoichiometry with just adding in this equation here. Remember, the T does have to be in seconds. All right, in our second example here, we are going to calculate the mass of the aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the electrical current is a 10 amps. All right, so a couple of things that we need to do. We could write out the full reaction, or you could just write the half reaction that we're concerned about. So you could do it either way. So if we just write the half reaction that we're concerned about, we know aluminum is +3 ion. So that will have to get reduced to make aluminum metal. Or you could write out the full reaction. If you did the full reaction, that would be aluminum chloride, liquid. So that's going to be happening at a high temperature again because it's a ionic salt, so its melting point is going to be very high. The reason why these happen in molten solutions versus aqueous solutions is because if the water was present, then the water would actually react before the metal ion did, and then you wouldn't get the result that you had wanted. All right, so that would have to be chlorine gas. So Hofbrinkel, so it's got to be Cl2. So then we would need balancing. That would be a 3. That would be a 2. That would be a 2. When we go to write our half reactions, either way, we are going to have the same ratio of aluminum to electrons, because here we would have 6 electrons, so 6 electrons per each 2 aluminums, or 3 electrons per each 1 aluminum. So either way, it's the same ratio. Now I'm gonna erase that just to give us a little bit more room to work. Okay, so first thing I would do is I would start with that new formula. And again, you can do these all in one step if that's what you prefer, but I kind of prefer to do it in 2 separate steps. So I know my current, that is 10. Again, I am looking for the coulombs, and my time is 1 hour. So 1 hour would be equal to 60 minutes, 60 seconds in a minute. So that would be 3,600 seconds. So then Q would be 10 times 3,600. So it would be 36,000. Cool. So then I would take that 36,000 coulombs, put that over 1. I gotta cancel coulombs. The way I cancel coulombs is I use Faraday's constant, 96,485 coulombs per every mole of electrons transferred. In this reaction, I am transferring 3 moles of electrons, again from the half reaction, to produce 1 mole of aluminum. Again, if you had done this from the full equation, it would be 6 moles of electrons per every 2 moles of aluminum, which is still the same ratio. All right, and then lastly, we got to get rid of moles of aluminum. So then we just multiply by the gram formula mass of aluminum, which is 26.98. And then we can check to make sure our units all worked out, which they did. And then we pick up our calculator and calculate. And I get 3.36 grams of aluminum. So that's how much aluminum I can get if I let this react for a full hour while passing a current of 10 amps through the molten aluminum chloride. Again, the reason why it's got to be the molten and not aqueous is because the water would actually react if it was the aqueous. All right, briefly want to go through electroplating since that is a common application for electrolytic cells. So that's a process where you take a cheaper metal and maybe even a stronger metal like stainless steel and cover it with one of your jewelry metals like platinum, gold, silver. So this way you have a silver coating, but it's stronger than silver and less reactive than silver, but it still gives it that silver or gold coating. So when we have electroplating, those are supposed to be arrows. If we are silver plating something, basically silver is reacting at both the anode and the cathode. The anode has to be oxidation, the cathode has to be reduction. So at the anode, the silver metal is getting oxidized, and at the cathode, the silver ion is getting reduced. The cathode is always going to be your object. So in this case, it would be the spoon because you want the silver metal to end up on the object. You also need a solution of the metal that you're plating on there. So if you're silver plating, you would probably see silver nitrate because that's a soluble silver solution. So the silver ion would be present. Then we would also need an actual piece of silver in order to do it, and that would serve as the anode. The cathode, again, is going to be the object that you are plating, so a piece of jewelry, and then a source of electrical current. All right, last example that we have here. How many seconds will it take to plate out 5 grams of silver from a solution of silver nitrate using a 20 ampere current? So if we write our reaction, again, we can just write the half reaction that we care about. So we have the silver ion that would be present from the silver nitrate plus an electron, so it's getting reduced to make the silver metal. We are starting with our grams this time. So this is a little bit opposite of the last 2 examples that we did. So we would start with the 5 grams of silver. We would need to turn that into moles of silver. So on our periodic table, we would find the atomic mass of silver, and that is 107.87. You'd be fine to say 107.9. Then we would do the 1 mole of silver is produced with 1 mole of electrons. So again, that comes from the half reaction. So if this was aluminum, which makes the +3 ion, then it would be 3 moles of electrons. So make sure that this comes from the balanced equation. And then we would do 1 mole of electrons correlates to 96,485 coulombs. That would give us coulombs, and then I'd put that into my I equals Q over T formula. Or again, you can do this all in one step, whatever way you find easiest for you. And that would give us 4,472 coulombs, which if we were rounding this step, it would be 4,500 coulombs. We are looking for time. My current is 20. The coulombs is 4,500, and T is what we are looking for. And so I get about 220 seconds. Make sure when we are doing a problem like this that we pay attention to what unit they wanted. You know, if you wanted minutes or hours, then you would make sure that you put the appropriate conversion in there. So this finishes up chapter 20. Again, our big things are just knowing some of your basics about redox and electrochemistry, then figuring out the voltage using the standard reduction potentials, the relationship between the voltage and delta G, and then also that you can use that to find K, the equilibrium constant, and then doing these electroplating or electrolytic examples, which is really just stoichiometry with that added step in there.